All right, so we have dealt with linear motion. That was basically the first couple chapters. We've gotten to rotational motion. Now, let's get into harmonic motion. And let's get a common vocabulary. So basically, we're dealing with waves. Frequency. Number of oscillations. Oscillations. Usually per second, but I'm just going to write down generically for unit of time. In other words, how frequently something happens. Well, it happens 5 times a second. So that would be oscillations per second. Any type of repetitive motion has a frequency. I use oscillations because that's physically what we'll be dealing with here, but it doesn't have to be oscillations. It can be anything repetitive. The symbol I use for frequency is a lot like the F I use for friction, if not the same F I use. Now, this does run into some issues at some point, not for this class because I don't duplicate it that way, but if you're looking at other textbooks, there's a difference between frequency distribution and frequency. And so F is often used for frequency distribution. So they needed a different symbol for frequency. And so if you're looking at another source, one of the symbols they use, the most common symbol used for frequency that's not an F is the nu. The Greek letter, lowercase nu. The trouble is that the nu looks a whole lot like a V. There's an equation which we will derive, it takes about 10 seconds to derive it, that V is equal to frequency times the wavelength. But if you're using a nu for the frequency, this equation looks like this. Now, some fonts that are used by textbooks, it actually looks like this, where the nu in that particular font looks more like the way I make my V's, and their V looks more like the way I make my nus. So when I'm looking at a textbook and I'm trying to figure out which one is this, I look for this equation here to try to figure it out, because I know it's going to be the V is equal to the lambda times the wavelength here. And so this tells me, okay, so this textbook uses font that way. This is why I use F. I don't want you to confuse your V's and nus. But I bring this up mainly because if you're looking at another source, it can be confusing. My first year here, I was sitting in my office and one of the nanotech students came over and she could not figure out why there was a V in this equation. And I looked at it and I thought, my first thought was, I don't know why there's a V in the equation. Then I thought, oh no, that's not a V. The SI unit for frequency is the Hertz. Named after Hertz. Clever the way they did that. Wavelength. The symbol is the lambda. That's the symbol I'm using over there. How far a wave travels. In one period. I'll do period next. So period is basically how long it takes to make a wave. The SI unit for wavelength. Anyone want to take a shot? It is a length as a hit. Yep. If I heard you correctly. is a capital T. We've used that period, the capital T for period when we're doing centripetal motion. The SI unit for period.
Time or seconds.
Yeah, the SI unit would be seconds. It is a time. And this is the time for one oscillation. The time for one oscillation of repetitive motion. So if I'm creating waves, this is the time it takes me to create a wave. So frequency is the number of, if we're talking about waves, let's be specific on waves here. If frequency is the number of waves per unit time, and period is the amount of time per wave. So frequency and period have a very firm direct relationship there. The fact that frequency is equal to 1 over the period. Or 1 over the period is equal to, try that one again. Or period is equal to 1 over the frequency. Or using the math lingo, they're reciprocals of each other. Using longer math lingo, they're multiplicative inverses of each other. Using the inverse relationship lingo, frequency times period equals 1. Amplitude. Generically, it could change depending on the situation. The SI units of amplitude depends. Depends on what kind of wave. Sometimes it's just physically, that's you're looking at a wave and you see how high up it goes. In which case, if you're dealing with a length, it'd be meters. Sometimes amplitude, you're talking about currents, in which case the amplitude would be in amperes. You're talking about voltage, in which case it would be in volts. It just depends upon the situation. So it is, I'll put distance in quotation marks here because it really does depend upon the situation. Distance from median to peak. So if I have a wave here, a median, that's my amplitude right there. And then the last one of the basic vocab words, angular frequency. The symbol is an omega, the exact same thing as for angular speed. The SI units of angular frequency are the exact same units for angular speed. Radians per second. Angular frequency and angular speed. I've never run into a situation where there was a distinct difference between them. There's a subtle philosophical difference between them, but you can always treat one like the other. To the point of, if I have, let's say I have some sort of arrow that's spinning around. So pivoting about the middle. The frequency would be how many times this arrow goes around per second. At least if I wanted my frequency in hertz. How many times the arrow goes around in seconds. The actual value of, no, we'll get to that part in a moment. As it spins around, its angular frequency would be the same as the angular speed of this thing zipping around. So the angular speed is the angle divided by the period, the angle divided by time. And if it's going around once, the angle is 2 pi, and the time is the period. So the angular frequency is just 2 pi divided by the period. Which, and since 1 over the period is the frequency, this is just 2 pi times the frequency. So we have another relationship here. Omega is equal to 2 pi times tau. All right, questions here? All right, the equation I just erased, let's derive it now. What is speed? What's the basic math definition of speed?
Distance over time.
Say it again.
Distance over time.
Yeah. So if we're talking about a wave that's being produced, I got a long coil here, and I'm just oscillating back and forth. The time it takes to create one wave is a period. The distance that it travels is the wavelength. So I have speed is equal to the wavelength divided by the period, which is the wavelength times 1 over the period, which is the wavelength times the frequency. And so that's what I written up there before, that the speed is equal to, whichever one I put first, depends on my mood. So we got a couple of relationships here. We got that frequency is 1 over the period. We have angular frequency is 2 pi times the frequency. And we have speed of a wave is equal to frequency times the wavelength. And any more that we have here? No. I guess I could put period is 1 over the frequency. That's it for the generic vocabulary of waves. Now we're about to talk about the types of waves, so a little bit more vocabulary, and then we'll actually do some physical examples. Actually, we'll do one physical example in the middle of our types of waves. Let's see, let's erase the stuff I started with. All right. So when we're talking about waves, there's two basic types of mechanical waves, which is what we're doing right now. There's another type of wave called an electromagnetic wave, that's second semester. But the two types are transverse and longitudinal. I'm parenthetically down here going to put down surface wave. There's a third type that some textbooks include. I don't think ours does. But some textbooks will include surface waves, and I'll talk about why a lot of textbooks ignore it. Now, whenever you have a mechanical wave, so these are mechanical waves, what makes them mechanical waves is the fact that they require a medium. You need to have, it has to travel through something. Unlike the electromagnetic wave, which doesn't have to travel through anything. The self-propagating wave, they can go through a vacuum. Mechanical waves do require something to move, physically move. So a transverse wave, particles or whatever the medium is, particles move perpendicular to the wave motion. Longitudinal, it's the other one. They move parallel. So, do a quick example of these. The slinky. All right, so I want you to sort of, what I'm gonna do is I'm gonna release some of the coils at the top and just sort of, hopefully you can see it. When I release coils, what did you see? Sorry? It seemed like they moved down. All right, anyone else?
It was like a little smoke cluster and then just going down.
Say again?
It was like a little smoke cluster and then going down together.
All right, and I assume that's what you were seeing also. Yeah. So the wave, you could treat it this way, that the wave you saw was that small little cluster that moved all the way down and then bounced back some part of the way. For those who didn't see it, like, we'll see it this time. To me, and apparently to at least two of you, there's something that seems to go down and then bounce back up. That is a longitudinal wave, because the particles in this case are the coils, and the coils are just moving this way. That's parallel or anti-parallel to the actual movement of the pulse. Now, that